Okay. So, now we will go to the third system. So, we did passive scalar, stably stratified flows, now we will go to thermal convection. So, this is another illustration of scalar, temperature being coupled with velocity field. So, turbulent thermal convection. So, system is very similar except, so let us look at the temperature in terms of temperature. So, hot below, no, convection means you heat from the burner, heat below, but cold at the top. So, this is slightly specialized, is not like heating water in a container, in a pan, but you also put a lid at the top. So, hot plate, cold plate above. So, there are two plates. So, this is so much simpler because you do not want to deal with the surface at the top. So, it is to simplify our life in analysis, is assume that there is a plate at the top as well. So, there is a temperature difference. So, T bottom, T top, the temperature difference is called delta. T top, T bottom minus T top is delta. So, T bottom is bigger than T top. What about the density? Which is denser? Above is denser, right? Because we know the density is minus theta, minus temperature. So, hotter is less dense, right? Warm water is less dense. So, it is a system which is opposite of stable stratification. That is why it is unstable. So, the top guys comes down and the bottom guys go up. So, the hot plumes, they go up. Why? Because it is lighter, it just wants to go up, and the top one which is colder, it comes down, and that creates a roll. Okay. And some of you already done in your project, and like so total temperature I write as this linear profile of temperature plus fluctuation. Okay. Same idea, like for density we had rho bar z plus rho, now we do the same thing here as well. Okay. So, theta is 0 at the top and bottom. So, theta is the fluctuation over the linear profile. The equation will be very similar to what we wrote for density. So, this is the buoyancy Fb, force by buoyancy, okay, alpha g theta. Alpha is the expansion, thermal expansion coefficient, and theta equation is this. Now, if I do the linearization, what will I get? So, some of it we already done, no? Linear stability, it is a growing solution. So, sign will come as a plus sign. So, if I do u z double dot, if I drop the pressure term plays a role, we did it in there, but let us just for simplicity dot theta dot, but theta dot will be u z from here. So, this becomes u z with a plus sign, delta is positive. So, now it is a growing solution, one decreasing, one decaying, one growing, but growing will win. So, this is unstable, but stability is hampered by the viscous term, right. So, this we done in the past. So, you agree that this is unstable, and naturally precisely because hot thing is going up and cold is going down. So, it will make it unstable. Okay. So, if del dot is 0. So, what is sign of u z? I think some of you correctly said. So, u z, so hot fluid theta positive, u z is positive, right. So, theta positive means is hotter than the ambient. So, there is ambient temperature. So, at this point there is a T bar local the planar temperature. If it is hotter, then it will go up. So, theta in u z has the same sign. So, u z theta must be positive. If theta is less than 0, is colder than the mean at that level, so it will come down. So, u z is negative. So, this implies that u z theta is greater than 0, correct. So, what is sign of Fb? So, energy, kinetic energy injection rate, sign of this should be positive, because you remember I wrote alpha g theta u z, that is the force, sorry, not u z. So, z cap dot u will be u z. So, this was z, the positive sign, this is a positive sign there, times u vector, that gives you alpha g theta u z. If I do the average, I get, sometimes it can be negative, In fact, we have situation where it becomes negative for short while, but over average is positive. Okay. So, what should happen? So, I think quickly I go to the, forget about this part, I think I will skip this one. So, let us just go to this one. So, what should happen to the flux? So, remember this d pi by dk in the inertial range. By the way, for thermal convection we do not apply any external forcing, buoyancy is good enough to drive the flow. If you just wait for some time, it will become steady. So, d pi by dk is fbk. In the initial range I drop the viscous term, so this is positive. So, my flux must increase with k. Okay. So, I expect the flux to increase. So, this is k in the x axis, I expect the flux to increase. At some point buoyancy will become weak. So, motivated by Bolzano-Volkoff, you say, well, maybe it will become flat after some time, and then dissipation takes over and it will become drop like that. Okay. So, this idea is obvious, but people didn't have this idea. In fact, there are names like Folkovich, Procaccia, Labov. So, the paper in 1991, there are two papers where they had argued in by using field theory in somewhat complex way, but their calculation has one glitch, which is very important glitch. They had claimed that FBK is negative. It is following from some kind of influence from Bolzano-Volkoff, not the physical intuition. So, physical intuition is like everybody will agree that u z and theta are the same direction, so FB is positive. So, it was a mistake, and as a result they had argued, in fact the big community, everybody believed that Bolzano-Volkoff theory should also work for thermal convection. So, spectrum must be minus 11 by 5. So, these theories claimed that thermal convection should give you minus Bolzano-Volkoff. So, Bolzano-Volkoff minus 11 by 5 and pi u, remember, 4 by 5. So, spectrum should decrease, but from this input what do you expect? Spectrum should increase, cannot decrease, because you are supplying. So, it is like philanthropy in the system. So, no corruption, but people are adding money, their own personal money. So, what will happen to the supply at a small scale? If the money has to flow from large scale to small scale, if you keep supplying, it is like not leakage, but injection into the pipe flow. So, more water will reach at the right end. So, flux should increase with k. In fact, so we got this idea in the 2014 paper, which Ananda was also there, PRE, with Abhishek was the lead simulator. I mean, he simulated with a lot of effort on, that was 1000 cube simulation with our code Tarang. So, we simulated, so I will show you the plot, okay. But and we were looking for it, increase in flux. So, we are saying, well, FB should be dominant because buoyancy is strong and should do it, but we never found this increase. We almost found flat flux. Flux does not increase, flux remains flat. Now, it turned out that there are reasons why flux should not increase, should not decrease first of all. So, this is out. So, nobody should say that it will decrease. So, this is definitely wrong, but it does not increase either. It increases marginally. The reason why it does not decrease, does not increase, is in the full equation we have u dot plus u dot grad u is minus grad p plus buoyancy term alpha g theta z cap plus viscous term. So, there is another student in our group, Ambrish, okay, Ambrish Pandey. So, he simulated, so we looked for all the magnitude of all the modes. So, some of it is accidental and we are looking for it. So, what did we find? So, this A, B, C, D. We found, so you expect buoyancy to be strong. So, that means C must be comparable to B, pressure gradient. So, the finding was that C was much less than B, in fact order 1/10. We know the number for Prandtl number 1 simulations. So, that means this term can be ignored. It is there because that is what supplies energy. If I turn off the buoyancy, then it will just decay, but it maintains the steady state, but it is really pressure gradient which is driving the flow. So, this is paper in 2016. So, we computed all the stuff. So, schematically pressure gradient is driving the flow. If this is the magnitude, buoyancy is 1/10. So, this Fv, this is pressure gradient, and dissipation in the opposite direction is small d, d viscosity. Is that okay? So, this is telling us that buoyancy is, though important, is weaker than pressure gradient. So, what does it mean? It is like hydrodynamic flow, where the pressure gradient is the dominant flow, dominant force, right. In hydrodynamic, pressure gradient wins the viscous term in the inertia range. So, that is why we get 5/3. Okay. So, the spectrum is basically what we get is, so this normalized spectrum. So, we multiply E k, this one is multiply E k, k 5/3 is flat. What does it mean? U k must be k minus 5/3. Okay. This one is multiplying U k by 11/5, is increasing. That means U k is not going as minus 11/5. If you put minus 5/3, then it will be increasing function. This is increasing. So, this is ruled out. Okay. So, this is just our eyes, normally the flat line is easier to convince, you know. Okay. So, this is on 4000 cube, again simulated by Abhishek. So, this came in 2017 New Journal of Physics, and you can look at the flux. This is kinetic energy flux for you is flat, no, I mean this is really flat, and this is pi theta. So, it turns out we can also define the temperature flux, which we did it like in the lecture I showed you. You can compute them, and that both of them remain flat. Okay. So, this is the very clinching evidence that Kolmogorov theory, Kolmogorov spectrum, constant flux is what is observed for thermal convection. Okay. So, it is very different than stably stratified flows, and it better be, because the nature of energy injection into kinetic energy is different. Okay. And so Shashwat has done this structure function. So, what do you expect for structure function? So, these are so look at S3, this is S3. So, S3 is what is according to Kolmogorov theory, 1941, slope is 1, right, L to the power 1 minus 4/5 epsilon 1, and this is that 0.95. If you look at 11/5, then you will get different zeta 3. So, this is for kinetic energy. Okay. So, we have not done for temperature. So, this is delta U cube parallel for third order. Okay. For higher order, you put the way with delta U to the power q, and it fits very well. So, this is Shay-Levesque theory, which I mentioned, but I did not describe in detail. So, Shay-Levesque is good for hydrodynamic turbulence, it fits very well. But you see RBC also fitting very well with the Shay-Levesque model. That means this structure function is telling us that hydrodynamic turbulence and thermal convection are similar property of turbulence, and it is I mean basically in the same lines. Pressure gradient is driving the flow. Now we can also look, so this is the technical part. So we look for temperature spectrum. Now I will not explain this. We get this funny structure, this one, 2 lines. Now these 2 lines bothered me for 6 months actually. I really didn't know why these 2 lines are coming. This is coming in a simulation, and you always suspect there is something wrong with the simulation. It turns out this is very physical. This is coming from physical region. This is correct. And why it is correct? Because there are 2 walls, hot wall and cold wall, and the temperature has mean profile. So theta, if I do the average over planar average, so theta overall, if you do the whole volume, it is 0. If you do the planar average, it is not 0. This is not equal to 0. Okay. So in fact it is easy to see. So let me just write this. So T of temperature I wrote as T bar of z plus theta, right? Yes, I mean this is what I wrote. If I do the average, planar average is integrate over xy. So this becomes T of z is this is same plus theta m of z. So T of z for temperature, we know for thermal convection it looks like this. So this is hot plate and cold plate. So temperature decreases rapidly, is constant in the middle, and then decreases again. Okay. So near the plate there is sharp drop in temperature. Now this is called boundary layer, okay, so which we will not discuss in this course, this is called boundary layer. So near the boundary, anything layer where things change very sharp is called boundary layer. So boundary layer temperature drops by half. If the whole drop is 1 unit, so half at the bottom and half at the top, and in between is constant. So what do you expect for theta mz? Theta mz will be Tz minus T bar z. In the bulk, what is that? So if it is, let us assume this to be 1 and this is 0, then this is half minus T bar z. I will not explain it, but it is dropping linearly, is 1 minus z. So you see theta m has a profile which is half minus half plus z. If you do the Fourier transform this, I am not going to get 0. So this is the Fourier transform, this gives you that top line. So this we show it in our paper. So the mean profile of theta m is giving the top line, and the remaining modes, Fourier modes, are giving you the bottom line. Okay. So this is what I say, that wall matters in turbulent flows. You put a wall, then you expect something different. So Kolmogorov theory is of course very beautiful, but it does not explain lots of phenomena. So wall, so my phrase is wall matters for turbulence. You can't say homogeneous isotropic flow is a theory and rest all are like minor theory. So this is, we have this grand unification, or we have like universal theory. So I gave a colloquium which I don't know, some of you are not there. So one theory is not going to explain everything. In fact, I am strongly disbeliever of that idea that one theory can explain everything. So Kolmogorov theory is nice, but it only works as a homogeneous isotropic turbulence. Of course, it gives idea about how to use flux, what does flux do, but one idea is to explain everything like what we have in particle physics. That's not, doesn't work. Okay, here wall is important. Okay, so stop. Thank you.